Okay, I'm recording now. Is the sound okay? Can you hear me all right?
Yes.
Yes, we can hear you.
Okay, let's get started. No, subtitles. Okay, let me start asking you if you have been able to register. According to my lists, there's still some people pending. The UCM people told me that they've reopened registration, so now you should be able to register to the course. Has anyone here had any problem with that? No problems for the people here? Okay.
Daniel,
yeah. Yes.
do you have any list of who is missing to register? Because,
Yes.
for example,
Yeah,
I registered,
I have
and
that.
I'm not sure if it's all finished or not. Like, if you could confirm.
Let me share with you
Perfect.
the persons. Okay, let me start presenting now. I'm opening my list in the UCM webpage where I can access it. Let me accept this person first. Yeah. So let me tell you the list of persons who have registered according to my list. So it's Ali Ufuk, Haritz Gamarra, Sergio Jaimes, Cristina Jarillo, Sergi Juárez, Daniel Portuondo, Josep Puig, Carlos Sánchez, and Eugenia Toro. This is 9 persons.
Quite a lot of people here are missing right now.
Yes.
For example, me, Jordi, Sergi.
But have you tried to register?
We did register, yes. We did register.
Okay.
But right now,
then,
the issue we're getting is that when we log into the page, I don't know, it gets some kind of error, and
okay, then the problem must be mine or with the UCM lists. So I'll ask them, but it's okay to know that you've been able to register. So for you, that's okay. I'll ask them and let you know if there's something misses or something else you must do. Okay, thank you. Let me share my screen again. Okay, let's start with the work for today's session and the previous work that we asked you to do if you had time. So first, we told you to, well, this is the list of tasks to do before. Let me do this a bit bigger. This is the list of things that you were supposed to do. So review input, output, and Verilog concepts. This is up to you. So whatever you need, each of you, you were given a textbook that we recommend. You can find lots of information in the internet. So I assume that you've done this part. view the RVFPGA input-output video. This is a video that describes in detail the architecture of the input-output system and the whole system on chip. And it gives a lot of details about those things that we'll need for resolving the proposed exercises. So if you've been able to view the video and you want to ask any questions that you may have, you can do it now. My idea was to review quickly the slides presented in the video, but not to do the whole presentation again, as it's already recorded. So if you haven't been able to watch it, you can do it whenever you have time. I'll review the presentation, but let me know first if you want me to focus on anything or resolve any questions that you have before that. Anything you want to ask about the presentation? Okay, so let me go quickly through it. And if you want to stop me at any moment, feel free to do that, no problem at all, and ask me anything related with what I'm talking about. As I say, this is described in this video called Input-Output RVFPGA or something like that. And the link is provided inside the module 2. So let me go in there. So this is the video I'm talking about. It's as usually recorded in Spanish with my real voice and translated into English with artificial intelligence tools. And the video describes the RVFPGA input-output system in detail. These are the slides that I'm now presenting. So let me go quickly through them. Well, here the general system-on-chip theory is described, and here we have the system-on-chip that we'll be using. It's based on the VIR cores. Especially, we'll use the EH1 core, although there are some other cores in the family, EL2 and EH2, but we'll work mainly with EH1. This is surrounded by the VIR EH1 core complex, which adds some more things to the core, such as scratchpad memories, data and instructions, instruction cache, the interrupt controller, and some other elements. Then we have the VirWolf X SoC, which is also an open source SoC based on this core, and it adds some peripherals. Some peripherals that we'll use in these exercises, and this is surrounded by the tools to be able to run the SoC on the board, the Nexus A7 board, which I have with me, and you all should have also with you, and the different simulator tools that we'll be using, targeting different features, such as a virtual board, a trace, or the EH1 pipeline. So this is the general structure of the complete system that we'll be using, and which is based on the EH1 core. Well, these elements are described here. Links are provided for you to be able to access all these open source elements. If you want, it's not necessary that you go into these links, because everything is already provided in the sources that you've downloaded the last day. And here we describe in detail each of the levels of the hierarchy that we saw before, starting with the core and the core complex, then the system on chip, then another view of the system on chip, focusing more on the peripherals, and finally the RVFPGA Nexus, which targets the system on chip to the board, and the different simulation tools, BitBo, and well, here only BitBo is mentioned, but there are two more simulators, as you know. It's important to highlight here that the memory map is also provided here, and this can be useful for developing the exercises where you will have to communicate with the different peripherals. This lets you know the memory addresses where they are mapped. We're using memory mapped input-output here. Okay, so any question about the system on chip, the core that we are using? Okay, so then after that description, the GPIO that the system on chip includes is described. The GPIO lets us communicate with the switches and LEDs on the board. It's an open source GPIO provided by OpenCores. This is the link to the controller that we use here. Again, it's not necessary for you to go into this link, as it's already provided in the sources, but this is provided for reference in case you want to look at it. This is a general purpose input-output hardware controller that provides 32 pins. So it allows us to communicate with the 16 LEDs available on the board here. 16, I'm not sure if you can view my board like this. Let me see. Okay. So the 16 LEDs and the 16 switches. So it's a total of 32 peripherals, and it's 32 pins, so we can communicate with all them. These are the memory mapped addresses of the registers included in this controller, and thus these are the addresses that we'll need to read or write in order to communicate with the LEDs and switches on the board. And this figure lets us know how these pins are connected to the switches and LEDs. So this line here, for example, tells us that pin 0 in the GPIO module is connected with LED 0, the rightmost LED on the board. Then pin 1 is connected with the next LED, and like this till LED 15. And as for the switches, if we go from left to right, the pin 31 is connected with the leftmost switch, pin 30 is connected with the next switch, and so forth, till switch the rightmost switch. So this connects the 16 LEDs and the 16 switches with the GPIO module included in the SoC and shown here in this part. Okay, this is connected with the core through an AXI bus and also a wishbone bus. Note that two buses are used in the SoC, one for communicating with the peripherals, one for communicating with the core, and thus a bridge is needed in order to connect the two different buses. The reason for using two buses is that the peripherals that we're using use a wishbone bus, which is an open source bus typically used by OpenCores, and AXI is the bus used by you're all familiar with AXI bus. AXI is the bus used by the core, so we need to bridge to add a bridge to communicate these two buses. Well, this is an example of how to communicate with the LEDs and switches that I will skip. You have all the explanations in the video. So any question? And this is the table with the memory addresses for all registers, including the GPIO. The first 3 registers are the ones that we'll use in the initial exercises, and the remaining registers will be used when using interrupt-based input-output, which is in the final exercises. So, any question about the GPIO? No questions. That's probably good. So let's go with the next peripheral that we'll be using in the exercises. We'll use 2 peripherals on the board in the mandatory exercises, which are the LED switches, and also the one described here, the 7-segment display, this one. Many other peripherals on the board are supported in the SOC, and lots of exercises are provided in the complete materials, the RBFPGA materials. So those of you interested in using other peripherals can find more guidance and exercises there. For example, there is an accelerometer on the board that is also supported. There is a temperature sensor also supported. These 2 tricolor LEDs are also supported and explained in the materials, the UART, and some others. Okay, some of the peripherals included on the board are not supported, such as Ethernet or others, VGA, for example. This could be added if you want. It's not a simple task, but it's very interesting. If you want to add a different peripheral which is included in the board but not supported in the SoC, you could follow the similar procedure as the one used for the peripheral supported. So you could download an open source controller, include it on the Verilog sources, regenerate the bit stream, and then be able to communicate with it. It's a nice task. We've advised several final degree projects, master projects, doing these kind of things. So any of you who is interested, there's a lot of information, and we can try to help you. Anyway, let's focus on the exercises for today's session. So the next peripheral for the exercises is the 7-segment displays, which is described in this part of the slides. This is the typical figure of a 7-segment displays, which allows us to show different combinations, providing different numbers or letters as shown here. And this is the low-level details of how the peripheral is connected on the board. You can listen to the video and try to look for more information if you need it in order to understand how this is connected. I won't give details here now. You have the details in the video, so you should watch that and ask me if you have any questions. And this is the figure showing how the displays are connected with the EH1 core. So again, we can see here in this figure the controller, which is an ad hoc controller for this board included in the SOC. It includes 2 registers that we can access from the core using their addresses that are provided a bit later. And this is prepared for being able to communicate with these 7-segment displays included in the board and used as described in the previous slide. Okay, so this controller transforms or translates the information provided in the registers from the core to the information needed by the peripheral as implemented on the board. Okay. Again, more details are given in the video, so please look at that to understand how this is connected. more details about the implementation of the 7-segment displays controller. And a simple example is given here showing how to communicate from a program and from the core with the peripheral. So you have to use these two registers I mentioned before, the enables register that allows us to enable or disable each of the 8 digits provided by the peripheral. We can enable or disable each of them individually by using these 8 bits that that represent if they are enabled or disabled with a 0 or a 1. And you can also select what to write in each of the 8 digits with this second register called digits reg, and which provides with 4 bits for each digit the value that each digit must show in hexadecimal. So we can show all numbers from 0 to 9 and letters from A to F as in the hexadecimal code. Okay. And a simple example is shown here that is also provided in a Platform.io project that you have to download, and which again you have explanations in the video. Okay, I'll test those examples after the presentation. Well, some details about the Wishbone bus that I will skip. These are interesting, but you can look at them on your own, looking at the video. And finally, some details are given about how to use interrupt-driven input-output, because in the initial exercises, you will be using program-based input-output, which is simpler, but worse to use in most situations than interrupt-based input-output. So details are given here about how to use interrupt-driven input-output in this SOC. Fortunately, Western Digital provides a library for letting us use the interrupt controller and interrupt-based input-output. These are the functions included in that library, which is open, and you can download it from a link that is provided in the materials. Short description of each of these functions is provided in this table. Anyway, you don't need to go into the details of that library, but you only have to use the functions that are provided in the examples, understand how to use them, and then reuse them in your exercises. Okay, so the example is described in these slides and in the video. Again, you can look at the description in detail in the video. And it shows how, it explains how the provided project works with the input-output based input-output. Okay. So this is it for the input-output video that you have to watch. Any question? Okay, so if there are no questions, let's continue with the next task that you are supposed to do. Well, these are the tasks described here. First, you have to download another set of sources called alternative projects. These are the projects that you will use in this module and which were not provided in the initial sources. So please download this if you haven't done it yet. I have them here in my laptop. The alternative projects directory includes 5 projects that you will use for understanding how these peripherals work and for using as a base for your exercises. Okay. So the next task is to understand some of these projects, starting with the most simple one, which is the one interacting with the LED switches on the board. There are 2 versions, one in assembly, one in C language. You should look at both in order to understand both of them because you will have to use both in the exercises. So please look at both projects. Let me open one of them. For example, the LED switches example in assembly. You as done in the first session, as in the whole course, we'll use Visual Studio Code as our SDK. With the Platform IO extension, you already have this prepared in the virtual machine. I'm using this natively in my Ubuntu machine, but you can use it exactly the same in the virtual machine. Let me open the folder for that project, which is in the alternative projects and LED switches directory, this one. Let me select this one. It should open here. Remember always to open the platform.io.ini file, which configures everything you need, and specifically it configures the path to the bit stream and the path to the simulator. Okay, these two lines are important because they tell the project where the bit stream and the simulator are located, and if this is not correct, it won't work. So in my case, this is my home directory. I don't think this is correct. In fact, let me correct that because it's not called RBFPGA, but RBFPGA master UCLM. In your case, this is not Dechaver is my home. This would be RBFPGA for those of you using the virtual machine, and this is the name of the sources. Sorry, no, again, it's not that one. It's alternative projects, the one that we're using now, the one that I've just. No, sorry. It was correct. It's the bit stream, which is in the original sources. Sorry for that. Yeah, this should be correct. So now, if I go into the Platform IO button on the left, I will follow the steps forward. Uploading the bit stream onto the board first. Well, it needs some time for updating. Now, I will upload bitstream like this, clicking here. If the path is correct, which I hope it is, it will, it will, no, okay, it was not correct. Let me check again. Sorry for that. RBFPGA master, relator, sorry, SRC, and stream. Okay, it's not Dechaver, but Dani. I don't know my home in this laptop. Okay, this one. Yeah, this should be correct now. Upload with stream again. Okay, upload with stream. Okay, now it's correct. You can see here at the end that it tells you programming and the path to the bit stream. Now it's correct because it's picking the correct bit stream. In the previous upload, it was not correct because it didn't find the bit stream I asked it to look for, and it uploaded the default bit stream, which is located here. But we don't want that. We want to use this specific bit stream. Otherwise, it can give us problems. So now it's correct. It's programmed the correct bit stream, which is the one found in that path. Okay, be careful with that. So now the board is programmed with the system on chip, and now I can execute my program. So if I click here and I run, the program that included in this project, let's switch this program, will start running on the board. Going a bit. No, I think, yeah, okay. It disconnected here and does it reset it. So now it's not uploaded again. I have to upload the bitstream again. Sorry for that, because yeah, the problem is that this cable is not very good. Let's see. Okay. Let me close and open again. And change the table. Yeah, let's see if now it works. Okay, let's upload the bitstream again. It worked correctly. The bitstream gets programmed here. Now let's execute the program. Let's switch this program. Yeah, now it's working. So the program will stop at the beginning of the main function. And this is the program, which is very simple. It starts by configuring the GPIO as input or output as needed. So note that the switches are input peripherals, whereas the LEDs are output peripherals. The switches are read from the core. The LEDs are written from the core. So we have to configure each of them according to their functionality. So switches are input, LEDs are output. This all is explained in the video and in the materials, okay? So this is the part where we're configuring the peripherals, the LEDs and switches. This is an infinite loop which constantly reads the switches here, accessing, reading this address called GPIO SWS, which is the input register in the GPIO. So we're reading that register. So we're reading the switches information. And this part is the write of the LEDs. So we are reading the switches, and here we are writing the LEDs with the switches information. So if the switch is down, the LED will be off, whereas if the switch is up, the LED will be on. That should be the behavior of this simple program, reading the switches and writing the LEDs. So if as I start executing, when I invert the switch, the LED, the corresponding LED should also invert. Okay, that's the behavior of the program. Okay, so this you should test on your own board and see if it works for you, or you have any problem. Any question about this first program? Have you been able to test it on your board? Have you had any problems? Questions? Okay. Next program you're asked to understand and test is the one interacting with the simple program interacting with the 7-segment displays. It's called 71 7-segment displays CLang. There's the assembly version, and they are provided. No, sorry, there's not an assembly version for this one. It's only a C language version. It simply writes the number 71 into the 7-segment displays. So let's quickly test this program as we've done with the previous one. Let me stop running the previous program. Let me close the folder. And let me open the new program by opening folder. It's in Home, Alternative Projects, and it's called 71 7-segment display CLang. This one, I select it, I open it. Note that the fixing is already programmed in the FPGA, so you don't need to program it again unless you want to change it. But here it's not necessary. We'll use the same bit stream. So we don't need to upload bitstream, and we only need to start executing the program. So let's do that here, and we start executing. If everything goes right, the program will compile and start executing on the board. It will stop again at the beginning of the main function. There's a default breakpoint there, so the programs will always stop at that point. In this case, this is the program. Note that it's simply writes some information into the 7-segment displays. Why do I know that it's writing to the 7-segment displays? It's using these macros defined, this macro defined here, which writes to this address this value. So this address is the one for the enabled registers for the 7-segment displays, and this second address is the digits register for the second segment display. So these are the two registers controlling the 7-segment displays. First one controlling if we switch on or off each of the digits. The second one controlling what value I'm writing to each of the digits. So in this case, I'm enabling only the two rightmost digits and writing the number 7 to the first one, sorry, 1 to the first one, and 7 to the second one. If we execute it, it should do exactly that. You can see that it's been 71 is being written to the 7-segment displays, and the six leftmost digits have been switched off. Okay, the program after writing stays in an infinite loop. Okay. So this is the second program that you have to test. Have you been able to do that? Any question? Okay, so let's go to the final program that you're recommended to test, and it's using interrupt-based input-output. Well, it's first using program-based input-output, and then the same program uses interrupt-driven input-output. So let's go to the first one. The first one is using polling, also called or program-based input-output. It's instead of being the peripheral, you probably all know that, but let me remind what each input-output mode involves. So program-based input-output means that the core is continuously asking the peripherals if they have had any change. So for example, it's constantly reading the switches to see if they change at any moment. And the difference with the interrupt-based input-output is that in this one, in the second one, the peripherals are the ones responsible of telling the core that a change has been performed. So it's the switches, the ones that will interrupt the processor whenever any change is performed. Okay. This is much more efficient, as you know, because the core can continue doing their work, and only will that work be interrupted when the switches have any change. Instead, if the core has to continuously be polling the switches, it cannot do other tasks, or other problems can appear. So for the first example, the program-based input-output, polling is used. Let's test that program. Let me stop again the previous program. Let me close the folder. Let's open the new example called, these two projects are called similarly, but one has no interrupts word in its name. The other one has interrupts. Okay, so this is the polling-based program. Let's open it. Again, I don't need to upload the bit stream again. I just need to start running. As usual, the program will compile and will stop at the main function. There's been a problem here, which I don't know. Yeah. Let's see. Update. Now it's ready. Sometimes it takes a bit for it to update. And until that is done, you cannot start running the program. Okay, so now the program is running. It's stopped at the beginning of the main function. And let's see what this program is doing. The program first configures the peripherals. You can try to understand that on your own. You have enough information for understanding how this is done. And the important part is that there's a while loop which polls the peripherals, and whenever a switch is changed, this specific program will just read the rightmost switch. So whenever a transition from 0 to 1 is performed in the rightmost switch, the corresponding LED will invert. And at the same time, an increasing count will be shown in the 7-segment displays. So that's the functionality of this program. And we can test it by running it. So if we run the program, you see that the count is shown on the LEDs. And I don't know if you can distinguish that, but you can run it in your board. And whenever I switch the rightmost, whenever I invert the rightmost switch, the LED will change. Okay. Only 0 to 1 transitions are detected. Okay. Whenever a 0 to 1 transition is detected, the LED will invert. You should see this behavior. Now you can see that the count is very fast. Let's slow down that count in order to be able to detect an interesting behavior here, and which will let us understand the difference between polling and interrupts. So I'm just increasing this value in order to do a higher delay, and that will make the count go slower. So let me recompile the program and execute it again. No, it's not slow enough. Let's see now. I'm writing here 10 million, okay. Let's see, this is slow enough. Yeah, it is now. Now you can see that the increasing counter is much slower. Now the interesting thing here is to see that if, well, yeah, let me do it even a bit slower, because I want to switch to do a 0 to 1 and 1 to 0 transition in between two different values of the count. So let me do 100 million here. It's very slow, but it's the best for us to understand the problem. Now it's very slow. It's 0. It's now 1. So the problem is that when I invert the first switch, if I do the 0 to 1 transition and 1 to 0 transition in between two counts, nothing is detected. You can see that the LED has not changed. Okay. If I switch and the value increases, now it is detected. The thing is that the switch is only red when we reach the end of the loop. Okay, when we finish the loop and go back here, the switch is red. But if we're in the delay of the function, the switch is not being read. So changes are not detected. Okay. We have this problem because we are using polling. We are polling the peripheral, and we're not polling constantly the peripheral, but only at the beginning of each iteration. So if the polling of the peripheral is not seen by the program, the LED will not be inverted. Okay, and this program gets resolved when we use interrupt-based input-output, because in that case, the behavior is different. In that case, it will be the switch that will interrupt the core while doing its 100 million loop, iterations loop. It will be the switch that will interrupt the core to tell it that it's being changed and that the corresponding LED should invert. Okay? So if we now go to that interrupt-based input-output project, and first I must close this one as usual, then I must open the interrupt-based project, open folder, alternative projects, and this one, note that it's the Let's Switch 77 display interrupts CLAN project. If I open it, well, it's initializing. The problem here is that it's been very slow because internet connection is not very good here. Otherwise, with a good internet connection, this should be much faster. Okay, now it's prepared. So let me run this program. The program is much more larger because it has to configure the interrupt controller, and that requires several things to do. But you don't need to go into to understand that part. Okay, you can see the whole program here. You can go in detail in each function if you want, but the important part is here, the main function, and the ISR function, the interrupt service routine function. This ISR has been configured for being executed whenever an interrupt is detected. So whenever, in this case, whenever the switch goes from 0 to 1, an interrupt will be launched that will make this function to execute. Okay, is that clear? So this will execute, and when this executes, this will invert the LED. So we will not have that problem of missing switches or switch inversions, because now every time a switch inverts, the program will interrupt and will execute the interrupt service routine. Let me again make this much bigger. Stop and recompile and run again. Note that this button both recompiles and executes. Okay. If I run the program, the count goes very slow. But the difference now is that whenever I invert the switch, immediately the corresponding LED will invert. I can do it as many times as I want, and immediately the LED gets inverted, as you can see. Okay? Any question? Let me stop this. Yes, Joseph? I cannot hear you. Maybe it's my problem. Let me see. Let me see.
No, I can't hear him neither.
Okay. Joseph, you may have a problem with your micro. Yeah. Do you want to write it, or you want to use another one, another micro? Or you can write it in the chat. Yeah.
Dígale. Parla.
Okay, yes. Can you hear me now? Yes. Okay, yes, I have a question.
Yes.
So interrupts are faster than polling. What is there any situation where polling is actually more useful than interrupts?
I'm not sure if I understood your question. Were you saying, were you asking if there's a situation where polling is more efficient than interrupt?
Yes.
Okay. I'm not sure if there's, what I think is interrupt will always be, will work better. But in some scenarios, maybe we don't need interrupts to be used. Imagine we have an application where we only need the CPU to be reading the information from the peripherals, and we don't need nothing else to do. Maybe a polling mode would be enough to be used, and that would be good. Okay, it's simpler. It doesn't require an interrupt controller. It's simpler SOC. Okay, so it's not that it's more efficient, but that it's enough for our application, and thus we don't need to have the complexity of an interrupt-based system. Okay.
Okay, thank you.
More questions? Okay, so those are the tasks that you have to do for getting ready for developing the exercises proposed for today's session that you will be able to work in now. It's 5 exercises. The first 3 exercises are using polling and are asking you to modify the functionality of some of those given programs that we've just tested, the Let's Switches CLAN program, the 7177 displays program for including a different functionality. Okay, so you can use these projects as a base and modify them in order to get that new functionality. It's 3 exercises. The first 2 are mandatory. You have to do them and include them in your final report. The third one is optional, and you only have to do it if you want to get a better grade. Okay. Then exercise 4 and exercise 5 are using interrupts. So they start with the interrupt project, the one that we've just tested. Exercise 4 is mandatory. Exercise 5 is optional. Okay. In case you're interested in using other peripherals, you don't have the information here in the GitHub, which only includes the information for the course itself, for the micro-credential. But in the complete materials, the RBFPGA materials, as I said before, you have many other exercises working with other peripherals on the board. Okay? So for the micro-credential, these are the 5 exercises that you have to do. 3 of them mandatory, 2 of them optional. But if you want to use other peripherals, you can look at the whole materials. Okay. So now it's time for you to work on the previous tasks if you haven't gone through them, and on the exercises. I'll be here to try to answer your questions, resolve the problems that you may have, and that's it. I will describe, as usually in these sessions, we will start working on the session, on the work for the session itself, and then by the end, I'll describe the work to be done for the next session. Okay, so that will be, I assume, around 12:30 or so. So in 1 hour and a half, I will describe the work to do for the third session next Friday. Okay. So any question before starting to work on the exercises? Okay. I'm here. You can ask me whenever you want. Keep your micros silent, and if you want to talk, just turn them on, and I will hear you. Okay.
Thank you, Danny.
Thank you.